In section 2.8, we'll be looking at the algebra of functions, including function composition. In particular, we'll perform operations on functions, compute the difference quotient, and we'll look at function composition. First, we start with operations on functions. So just like you can add, subtract, multiply, and divide numbers, you can add, subtract, multiply, and divide functions. And you create new functions along the way. The notation looks like this. You have f plus g in one big set of parentheses. Then it says of x. The new function created is f plus g. Sometimes you give it a new name, and sometimes you just say f plus g, and that's one new function. By definition, the way you work with f plus g is to take the f function and the g function, and you add them together. And then the same thing goes for a subtraction. F minus g is a new function that is computed by taking f of x minus g of x. Thirdly, we have f times g of x. You take f of x and you multiply it by the g of x. Now this one is also written as fg of x without the dot, right? You just throw two things together. That means multiply in math. And then, of course, the definition would be f of x, g of x, also without the dot. So you might see this notation crop up somewhere. Fg is just f times g. No dot. And then f over g of x is f of x divided by g of x. Now, the one thing that you can't let happen here is the g of x be equal to 0. And that's the problem with you can't divide by 0. Now this one is also sometimes written what they call inline, like this. F divided by g, so f slash g of x. And you might see that if they were just going to write it out on a single line. F slash g of x, f of x over g of x. All right, let's see how to use these operations. Example 1. Let f of x equal 4x minus 3 and g of x equal to 7x plus 14. Find each of the following. So the first one is f plus g of x. So by definition, this is the f of x plus the g of x. So you're going to take f of x, you're going to add it to g of x. Now, what I would do first here is I would start with the f function, minus. And I would put it in parentheses, okay? I know what you're saying. You're saying the parentheses are redundant, and you're right in this case. But they will save you, especially on a test, if you remember to put in parentheses. And then you would simplify this. So the x is 4x and 7x is 11x. Minus 3 plus 14 is plus 11. So the new function, that is f plus g, is 11x plus 11. Let's look at part B, where it's f minus g of x. So that would be f of x minus g of x. Again, let's use parentheses. We would have 4x minus 3 minus 7x plus 14. And now, can you see the rationale for using the parentheses? The negative has to distribute to all the parts that are in the g. So it's going to be 4x minus 3 minus 7x minus 14, giving us a result of negative 3x minus 17. Incidentally, where have you seen the subtraction of two functions before? So this is a side note here. Remember, profit is equal to revenue minus cost. That's exactly what we're doing now. We're saying that there's a revenue function, there's a cost function, and when you subtract them, you get the profit function. Okay. All right, f times g of x. Please turn off your phones. F times g of x is f of x times g of x. So this would be 4x minus 3 times 7x plus 14. And you would multiply out this result. You get 4x times 7x plus 14. If I distribute the 4x, minus 3 times 7x plus 14. You would distribute the 4x, so that would be 28x squared. Let's see, 14 times 4, 56. So that's 56x. Negative 3 times 7x is negative 21x. Negative 3 times 14 is negative 42. And then you combine like terms. 28x squared plus 35x minus 42. Now I chose to use the distribution method of multiplying. If you're comfortable using FOIL or whatever it is that you know, then you go ahead and do that. The point is you got to multiply it out somehow. So whatever you need to do to get that, you do it. Lastly, f over g of x would be f of x over g of x. And that's 4x minus 3 over 7x plus 14. And that's it. Nothing you can do to that one. That's as simple as that one gets. All right, page 2, example number 2. Let s of x equal x plus 3 and t of x equal x squared minus 4. A, find s minus t of negative 5. So this one we have a number that we need to evaluate. So this would be equal to s of negative 5 minus t of negative 5. And then you just need to compute what s of negative 5 would be. So the function s says to take x plus 3. So we're going to take negative 5 plus 3. And then we will subtract the result of taking negative 5 and evaluating it in the t function. So that would be negative 5 squared minus 4. This would be negative 2 minus 21. And the answer is negative 23. So instead of having a variable and finding an explicit function for the sum, difference, product, or quotient function, we went ahead and evaluated it at the number and then took the sum, difference, product, or quotient of those results. Part B, find s over t of 2. So this would be s of 2 over t of 2. And you would simply evaluate 2 in the s function, 2 in the t function, and then divide. Let's see if this is going to work. All right, so this would be 2 plus 3 over 2 squared minus 4. The numerator would be 5, but the denominator would be 0. And this is bad. This is can't have 0 in denominator. So this was that little warning that was at the side of the quotient function. You can do f divided by g, as long as the g of x is not equal to 0. Well, this is one of the points where it is equal to 0. So the ultimate answer for this is that it is undefined. Oops, undefined. So the new function s over t is undefined at 2. It's certainly defined at other points. It's just not defined at 2. So that leads us to a new question. And the question is, what are the domains of these new functions? So here it is. The domain for each of the sum function, the difference function, the product function, and the quotient function is the intersection of the domains for the individual functions f and g. Plus, for f over g, you must also exclude the values that make g of x equal to 0. So we did a section like this in chapter 1 where we had all these inequalities and things and sets, and we put them together through union and intersection. That is where that section comes into play now. You need to take the domains for each of the functions and find the intersection. Remember, the intersection symbol is the upside down version of that. So let's see how it works. Example 3. Find the domain of f plus g when f of x is equal to the square root of x minus 3 and g of x is equal to 1 over x minus 5. So first, let's start with the domain of f. Remember that there are two types of problems where we can have issues with the domain. This example is a perfect example. It has one of each of them. The first one was square root functions. You cannot take the square root of negatives. So the domain for a square root function is found by taking the inside, x minus 3, and setting it greater than or equal to 0. You can take the square root of a positive, and you can, yes, you can take the square root of 0. Square root of 0 is 0. Solving that, you get x is greater than or equal to 3. If you write that in interval notation, that's 3 to infinity. And if you look at the number line, put 3 here. I'll use the dot notation today. So it's the dot at 3 going all the way out to positive infinity. So the highlighted portion is the set of elements from the domain for that function. So I can take the square root of, when the function is x minus 3, I can use any x that's 3 or larger. No problems. Next, we need to find the domain of g. When you have a rational function, the domain is the set of elements that do not make the denominator 0. So we get x minus 5 is equal to 0. We're going to find the bad points, and then we're going to exclude them. This would be x equals 5. That's a bad point. So in interval notation, it would be negative infinity to 5, union 5 to infinity. If we draw the number line, then here's 5. The only thing we need to do is jump over 5. So I'm going to put an open circle there, and I'm going to shade the rest of the graph. So, and now the domain of the new function f plus g. Remember, it has to be the intersection of both of these domains from above. So I'm going to use the top one and the middle one there to create the bottom one. The intersection is where they have common shading. So there is no common shading on the left side. Common shading starts at x equals 3, and it includes 3. And then we have common shading until we get to 5. There is no shading on the element 5 in the second one, so we're going to have to skip that one, but we get everything between 3 and 5. And then going out towards infinity, we do have common shading. So the domain would be 3 to 5, bless you, intersection 5 to infinity, like so. The way to think about the domain for one of these added or subtracted functions or anything, it has to be elements that work for both functions that are involved. So the only elements that would work for both f and g are elements that are not equal to 5 and bigger than or equal to 3. And that's exactly what we have. Bigger than or equal to 3, but not equal to 5. Next, let's look at the difference quotient. So here we have a function f, and we're going to define what we call the difference quotient. I'll abbreviate the difference quotient with dq. So the dq, the difference quotient, is going to be used to find the slope of the secant line. Secant line. Now, you may remember we've done this before. We just didn't call it the difference quotient. We called it instead the average rate of change. And that's the same thing. The reason we call it the difference quotient now is because we're going to use some different notation, and it's going to be helpful when you get to your calculus class. So it's the average rate of change of f over x to x plus h. And I'll show you where these pieces are coming from. Let's go ahead and write on the graph itself. So this first point where we have the red line intersecting the function is the blue line. This point is going to be P, and P has coordinates that are x, and then instead of calling it y, we're going to call it the equivalent of y. We're going to call it f of x. So here is x, and then the y is f of x. Then we have this other point, which is q. And how do we find q? Well, q is going to be over here. Now, instead of calling this something like x2 or something like that, what I want to define for you is the distance between x and this new point. And we call that h. So if I start at x and I go over h, the new point is x plus h. Because you take the original point, add the distance. Can y'all put your feet down? Thanks. You start at x, you go over h, you get to x plus h. Because h is how far you're going over to the right. So the points, or the coordinates rather, for q are x plus h, and then the function value at that point, f of x plus h. All right, so now we can find the formula for the difference quotient. The difference quotient is no more than the slope function. We're going to take the y-coordinate at point Q minus the y-coordinate at point P. So it's f of x plus h minus f of x. And then we're going to take the two x values and subtract them. So it's x plus h minus x. There's one little bit of simplification that we can do. Notice that in the denominator we have x minus x, so we can get rid of the x's. But other than that, this has to stay. You can't subtract the x's from the top because they're being evaluated under a function f. So there is the difference quotient. You can also see now why we call it the difference quotient. The difference is the result of subtraction, which is what you have in the numerator here. And then the quotient is the result of doing division, which is dividing by h. Now, one area where I see students get messed up is they try to put subtraction in the f of x plus h. They try to put in f of x minus h. It's x plus h because you're going from a point on the left to a point on the right. Since you're moving to the right, you add. You're going to add the h. Okay. So the difference quotient is the slope of the secant line. It's the average rate of change in a different form, and this is the formula. You are responsible for knowing this formula. If you forget the formula during the test, all you got to do is remember this picture and reconstruct the formula. Now let me show you how to use the difference quotient. Example 4, find the difference quotient for f of x is equal to x squared. Then find the average rate of change of the function f over the interval 1 to 5. So first, let's find the difference quotient. Now, when you work with the difference quotient, more likely than not, you end up with another function with x's. It is possible, and there will be certain problems where you end up with a single number, but that's a very special case of the difference quotient. Usually, you end up with a function. So write out the difference quotient. Next, we want to find each of the three parts for the difference quotient. So f of x plus h, then f of x, and then the h on the bottom. My suggestion would be to use square brackets around each of the two parts in the numerator. That ensures that everything is in the right spot and that the negatives are going to get distributed correctly. First, you need to find f of x plus h. We've done this before. Remember, if you're finding f of x plus h, you take parentheses x plus h and insert it where the x is. So it's going to be parentheses x plus h, and then the function here is the squaring function. So then you square that. It is not x squared plus an h. That is not what's going on here. This is x plus h inside the function. So you need to take x plus h and then square that. Minus another set of parentheses. F of x itself is x squared over h. Now we have to work this out. Recall we have a little shortcut formula for doing x plus h squared. You square the first one. You square the last one. And the middle term is 2 times the first one times the last one. So 2 times x times h is 2xh. If you still need to work it out, feel free to do that. Minus x squared all over h. You will know that you have done the difference quotient correctly when you can get the following things to work out. You should be able to cancel some terms on the top. In particular, you'll be able to cancel all of the terms that came from the f of x part. That's the first step. And that leaves us with 2xh plus h squared over h. The second thing that should happen if you've done this correctly is you should be able to factor out an h from the top and cancel it with the h on the bottom. Notice that both terms have h's on the top. So we're going to factor out an h. and then we are going to cancel. And there is the difference quotient. It is a function. It's 2x plus h. And any sorts of stuff can happen with this difference quotient. So you'll get x's and you'll get h's, and you'll end up with this function. Now, for the second part of the question, it says, find the average rate of change of f over the interval 1 to 5. Yeah. So we are over the interval 1 to 5. So what you need to figure out is what value to use for x, and we're going to use x equals 1, and what value to use for h. Now remember what the definition of h was. H was the distance over to the next number. What is the distance over from 1 to 5? It is 4, right? So the h is the difference in these numbers. So h is equal to 4. And you just plug this in. So 2x plus h is the difference quotient. Evaluate that at the 1 and the h. 2 times 1 plus 4 is 6. So what that tells me is the average rate of change for the square function from 1 to 5 is 6. All right, let's look at example 5. Find the difference quotient for f of x is equal to 3x squared minus 4x plus 5. Then find the average rate of change of f over the interval from -2 to 9. So the difference quotient, I always write out the formula. I encourage you to do this as well, because that's a way to help you remember the formula later on. Muscle memory. We need to evaluate the function first at x plus h. So this is going to be 3 times x plus h, in parentheses, squared minus 4 times x plus h plus 5. Notice I've used a different color to highlight the x plus h, and so that you can see that it has to be put in for every x. There are two instances of the x here. It goes in for both of them, and it goes in as a grouping. It's x plus h in parentheses. The next piece is minus f of x. Oops. That would be 3x squared minus 4x plus 5 in parentheses. Again, you're seeing the necessity of using parentheses so that in the next step later on, the negative gets distributed correctly. This is divided by h. And now we work out some algebra going forward. The first thing I will do is multiply out x plus h using our little trick again. It's x squared plus 2xh plus h squared. Distribute the -4, you get -4x minus 4h, then plus 5. I'll leave this in parentheses for one more step. Next, I'll distribute the 3 and this negative on the right side. So on the left side we get 3x squared plus 6xh plus 3h squared minus 4x minus 4h plus 5. Distribute the negative, get negative 3x squared plus 4x minus 5 over h. cancel what you can. I've got negative 3x squared and positive 3x squared. I've got 4x and negative 4x. I've got negative 5 and positive 5. Notice that when I started looking for things to cancel, I started on the right side. That's because if you do the difference quotient correctly, each of the elements from the f of x on the right side should cancel with pieces from the interior. Let's rewrite what we have left. 6xh plus 3h squared minus 4h over h. Second part of doing this correctly is there should be an h that factors out on top, and there is. Notice that each of these three terms has an h. So we're going to get 6x plus 3h. This was h squared, so when I factor out one of the h's, I get an h left over. The last term was negative 4h, so that's going to leave me with a negative 4 over h. H's cancel. And that leaves me with 6x plus 3h minus 4. That's the difference quotient. There it is. The second part of the question was to find the average rate of change over the interval negative 2 to 9. So x is equal to negative 2, and the h is equal to what? Bigger than 7. 11. 11. You'd have to do, let's see, negative 2 to 9 would be 9 minus a negative 2, so it's 11. So this would be 6 times negative 2 plus 3 times 11 minus 4 be negative 12 plus 33 minus 4, which is 17. How many of you are science majors? A good bit of you, right? What do we call h in the sciences? Delta x. So if you see delta x, think of that in this class as the same thing as h. Delta, remember, is the scientific notation for change, and that's exactly what h represents. It's the change from one x position to another x position. All right, let's look at composition of functions. So, in addition to there being the 4 arithmetic operations on functions, adding, subtracting, multiplying, and dividing, boom, there's a 5th operation. And that operation is called composition. Composition is when you take the output of one function and you use that as the input of another function. So you're going to have 2 functions involved, could be more, we'll just use 2 today. And you take the result of one function and you use that inside as the input for another function. The notation for composition is a little circle. So it's going to be f composed with g of x, and the definition is going to be f of g of x. So notice how the g of x is inside the f of x. So you're going to evaluate f of x inside of g of x. Finally, composition works right to left, or inside out. So even though we write this as f composed with g of x, the first function you will be using whenever you do f composed with g is g. You start on the right side and you work your way back into toward the left. Now, here's a somewhat non-algebraic example. And this is a good way for you to think about composition. I call it breakfast. So how do you make breakfast in the morning? Well, you start with bread. So let x equal bread. And what's the first thing you do to bread? You toast it, right? So t is going to be the toasting function. What is the input for the toasting function? Bread, right? So t of x is you take bread inside the toasting function, and what do you end up with? Toast. You end up with toast. See? You end up with toast. Now, once you have toast, then what do you do to toast? Butter, right? So now we go again. So t of x is toast. B is the buttering function. And what do? You butter the toast. So is it b of x? No. B of x would be butter the bread. You don't butter the bread, you butter the toast. And what do you end up with? Buttered toast. Exactly. There you go. Now, how would you write this in composition notation? It would be B composed with T of X. Buttered toast. That's what you end up with. Now, suppose that X is not suppose X is not bread. What else could you put in the toaster? Like one of those little bagels, you could do that. So then you have toasted bagel. Then you run that through the buttering function, and you get toasted bagel. You could buttered toasted bagel. You could put butter on a bagel. You could also put with that little cream and stuff. You could do that. What about a little strudel? You could put a strudel, toasted strudel, and then you have the icing function. You could do that. You could have jam function. That's how composition works. So the main thing is you're taking the output from one function and you're using it as the input of another function. Now, does the order matter? Yes, the order does matter. So here's a great analogy, right? Could you put butter on bread and then toast it? No, because that'd be a mess. You get butter leaking out the bottom of the toaster, that's not going to work. So you could not do that. You have to do things in order. All right, let's take a look at example 6. Let f of x equal x squared minus 4x plus 1, and g of x is equal to x plus 2. Find f composed of g of 3. All right, so f composed with g of 3 is, by definition, f of g of 3. So first we need to figure out what g of 3 is. You do the inside first, and then you work your way outside. So g of 3 is 3 plus 2. 3 plus 2 is 5. So it's going to be 5 squared minus 4 times 5 plus 1, because now we take 5 and we plug it into the f function. Right there. And that's a 6. So again, you evaluate the inside function first, then you move it, take that result and plug it into the outer function. Let's try B, G composed with F, evaluated at negative 4. So that would be G of F of negative 4 we're using the same two functions as before. So I need to compute what f of negative 4 is. So that would be negative 4 squared minus 4 times negative 4 plus 1. If you work that up, you get 33. So then g of 33, you take 33 and you put that into the g function. The g function is x plus 2, so that's 33 plus 2, 35. All right, let's look at example 7. Example 7 says f of x is equal to 3x minus 12 and g of x is equal to 1 over x plus 2. Now we want to form the composite function and find the domain. So the composite function, f composed with g of x, is f of g of x. The g of x is 1 over x plus 2. So we literally say for the moment f of 1 over x plus 2. We then take the expression 1 over x plus 2 and we plop it into the f function. So that's going to be 3 times 1 over x plus 2 minus 12, because the f function was 3x minus 12. And then we simplify that a little bit, not too much. This is going to be 3 over x plus 2 minus 12. Now, to find the domain, you have to look at the domain of the first function that was used and the second function and the result of those. Now, the second function, you're not going to exclude the parts of the domain that make the second function undefined, but you're going to exclude the ones that would make it undefined after you plug in what the first function represents. Okay? So first here, the first function that was used was g. So we're looking at g first. G is a rational function. The domain of a rational function is the set of elements that do not make the denominator 0. So we set the denominator equal to 0 to find the bad elements. That's negative 2, and that's bad. So right away, negative 2 is out of the domain. Now the question is, what elements would make f undefined? F is a polynomial. Polynomials are continuous everywhere, so there is nothing that's going to make f undefined. So that's where the trail stops. So the domain of f composed with g is negative infinity to negative 2, union negative 2 to infinity. Let's look at example 7b. Find g composed with f of x and its domain. So g composed with f of x is g of f of x. And now we take the f function and we're going to evaluate that inside of g. So f was 3x minus 12. When that goes inside of g, we're going to get 1 over 3x minus 12 plus 2. Because g was 1 over x plus 2, simplifying the denominator, bless you, we get 3x minus 10. To find the domain of g composed with f, we first look at the f function. The f function, again, was polynomial, so there's no domain problems there. Next, we have to look at the result of putting f into g. Notice we're not looking at the g function itself. We're looking at the result of putting in f into g. That results in 1 over 3x minus 10, That's rational, so set it equal to 0. Solve for x, and you get 10 over 3. This is the only bad point. So the domain here is negative infinity to 10 over 3, union 10 over 3 to infinity. Once again, there is a bad point for g, but we don't get to solve just g. We have to look at the result of putting f inside of g in order to find any of the bad points. Finally, and this is for an example, you can compose a function with itself. What is f composed with f? So that would be f of x, which would be f of 3x minus 12. And then you take 3x minus 12 and you plug that into x in the 3x minus 12 from the same function. So it would be 3 times 3x minus 12 minus 12. 3 times 3x is 9x. 3 times negative 12 is negative 36 minus 12. You get 9x minus 48. So the composition function here is 9x minus 48. The composition is polynomial. The two functions that made it up were both polynomial, so there is no problem with the domain. The domain is negative infinity to infinity.